Section 3.9, Part 1, Linearization. So one of the real powerful uses of calculus is that it gives us a way of approximating functions that are constantly changing and are often quite complicated. And the main idea of this section is that you can approximate a function with its tangent line by using the derivative, and as long as you're close to a certain point where that tangent line occurs, the tangent line and the function will be very close to each other and will roughly represent the same thing and thus can be used for good approximation. So let me give you an example here of how this might show up. So suppose you're making pizza dough and you need the water temperature to be about 115 degrees when you add the yeast. If water's too hot, then it kills the yeast and it won't rise. And if the water's too cold, then the yeast doesn't activate and the dough doesn't rise either, and you get basically like a pizza on a tortilla, which, isn't very good. You want it to actually rise. So first you boil the water, and then you wait for it to cool. And you've got your little temperature gauge in this pot of water. And after 5 minutes, temperature is 170 degrees. After 10 minutes, it's 152 degrees. And for 15 minutes, it's 140 degrees. And then your son comes in, and he throws a ball, and it knocks the thermometer out of the pot, and it breaks on the floor. And while you're putting your son in timeout, you think to yourself, how am I going to figure out when this temperature will actually hit 115 degrees now that I don't have a thermometer anymore? So we want to use this information to estimate when the temperature will hit 115 degrees. So graphically, what's going on here is, let's say this is about 100, that's 200, this is degrees on that axis. And then over here we'll put time. So here's 5 minutes, 10 minutes, 15 minutes, 20 minutes, 25 minutes. And we can actually plot some points. So this is about 150. There's 50, so 212, that is the temperature at which water boils. So I can put a dot right there. That's 0 minutes, it was at 212 degrees. After 5 minutes, the temperature was 170, so that's 5 170s right about there, because this is 150. And then after 10 minutes, it's 152, so I'll go for 10, and I'll just put that right at about 150. And then after 15 minutes, it's 140. So we'll come up here, maybe right about there. So our curve looks like this. And we can basically assume that it's going to keep going this way. But I can draw that on there, but how can I actually get a numerical estimate for what's going on? So the first way we're going to estimate this is we're going to estimate with the line from 10, 152 to 15, 140. The idea here is if I take these 2 points, those are the last 2 data points that I had, and I make the line through those 2, that line will be approximately close to what I'm expecting my actual line to be. So this is to find the line between 2 points, I first need to find the slope. So that's rise over run, and that's my y2 minus y1, 140 minus 152, and then my x2 minus x1. So this comes out to being negative 12 over 5, which is negative 2.4. And now I'm going to write the equation for the line. That's y minus y1, and I can choose either one of these as my x1, y1 for this. I'll choose the second one. So that's y minus 140 equals m, negative 2.4, times x minus x1, which is 15 because I'm using the point 15, 140. And this comes out to being y equals negative 2.4x. I think that'll be plus 36, plus another 140 is plus 176. And the idea is, if I want to know when the temperature will hit 115 degrees, I just set 115 equal to negative 2.4, that should be a 4, x plus 176. Subtract that over, this gives me, negative 61 divided by negative 2.4 equals x. And when I do that calculation, so that's 61 divided by 2.4, says x is about 25.4. So that's estimating right around here at 25 minutes. But the problem is that this uses my last two data points, and that's not actually the best approximation possible. And the idea of this section is that I could find a better approximation by using the tangent line. So here was my last data point. If I actually draw the tangent line at that last data point, you can see that this gray line is actually much closer to the green line that we expect than it is to that red line. So I'll just say better estimate by using the tangent line. And luckily, we know how to find the tangent line by taking derivatives. And the term that we use for this is linear approximation, or finding a linearization of the graph. Those mean the same thing. And we have this definition right here that the linearization of a function f of x at a particular point p is the line L of x equal to f of p plus f prime of p times x minus p. Now, the funny thing about this is this actually comes directly from the point slope form of a line, which is y minus y1 equals m times x minus x1. Here, our x1 is just the point p. The y value at p is going to be, so the y value, that's our y1, that's what you get when you just plug p into the function f. And then our slope m is the derivative of the function f prime, and then you plug in the point p. So if I put all these in here, this is y minus, in place of y1 I get f of p, m is going to be f prime of p, and then x minus p, and then I add the f of p over to the other side, I get y equals f of p plus f prime of p times x minus p, and that's the same thing that I have here. The only difference is that this y they call L of x. They use the capital L to represent linearization. And if you want to forget this formula and just anytime I ask for linearization or linear approximation, you just do the tangent line at that point, that's perfectly fine. That's the exact same thing that we're doing here. It's just a different way of writing the same thing. And the idea is that we'll use this linearization to get an approximation of the function near the point p. The further we get from that point p, the less accurate the linearization will be, because it'll get further and further from the actual line.